Imogen, and this is my Lab 4 on Oscillations. For this lab, I've split it up into two parts, the introduction and experiment details. The purpose of the lab was to predict the motion of a mass oscillating on a spring, use tracker to analyze mass with respect to position over time, build a computational model of observed motion, and analyze change in energy. The system is the mass, spring, and earth, while no work/energy change are its surroundings. Some models and fundamental principles used were the spring force, kinetic energy, gravitational potential energy, spring potential energy, the energy principle, force due to gravity, and the velocity and position update formulas. The methodology behind this experiment was to edit the computational model based off the fundamental physics principles, insert X and Y position data as a CSV file, which would be used to run the code. Then once the code was run, compare and contrast the data and computational models. The preview of my results are written below: the initial position, mass of the object, weight and spring force, and calculations for spring constant and L0. Experiment details. And here we have the video of the analysis of the mass's motion using tracker. For the computational model, I used the initial mass along with the initial conditions which I got from tracker. I also added the gravitational force, spring constant, and L0, and starting on line 88 and forward, I used the formulas for kinetic energy, gravitational, and spring potential energy to compute the system energies. Next, I calculated the force due to gravity and spring force from formulas mentioned in the beginning, and then set net force equal to these two forces. Then I applied the momentum formula to calculate the object's velocity and position using the position and velocity update formulas. And on line 130, I updated the spring formula as shown here. And lastly, I calculated the change in energies using the same three formulas from the previous slide. Based off the code from my previous two slides, here's a video of my computational model. As you can see, the object moves back and forth, creating an oscillating motion, and the mass gains and loses energy but twice as fast as UG and US. And if you look in the middle, you see the orange line, which represents the change in energy, and since the entire system is mass, spring, and earth, there is no energy change. Graph comparisons. First, we're going to go over the change in energy versus time. The gravitational potential energy and the spring potential energy more or less switch back and forth, as seen by the fact that they oscillate roughly opposite to each other. However, let's not forget about kinetic energy, which also oscillates as the mass speeds up and slows down during its motion. What's interesting about the orange line is that it's plotting the total energy change, which suggests that there is no change in total energy for the motion of the mass. More on graph comparisons. For both graphs, they line up pretty well. However, for the x position versus time graph, we can see that the two lines deviate for a bit later on as more time passed. For the y position versus time graph, the data lines up pretty well except for the max and mins, which could have happened if I overcalculated the initial displacement in the y direction. Thus, all subsequent displacements were greater than what it was actually supposed to be. Three possible errors I want to talk about are human errors. So when I was plotting the data points in tracker, calculating the spring constant using the time period for oscillation, or the low frame rate or video quality causing miscalculations, which could have explained why the graphs from the previous slide tend to deviate from each other as more time went by. Is the energy principle satisfied? Yes, because no work was done to the overall system. E was equal to 0, which means that no energy was changed between the system and its surroundings. UG and US are oscillating within the same period. Although they are in opposite phases, K is shown increasing and decreasing in line within the peaks of UG and US. Another part of the discussion was the calculation of oscillating periods based off X and Y position data. Written below are the calculated X and Y positions and the difference between these oscillations impacts spring force, calculation of spring constant, and spring potential energy. And incorrect or difficulty tracking can cause this difference, and since these periods are not the same, they could be due to the period in Y, which represents the vertical motion of the spring, and X, which represents the horizontal motion, such as the pendulum. And the time period between these crests or troughs versus time is equivalent to the time to complete one cycle, and I found the average oscillation period by finding the average of 3 cycles and dividing them by 3. Ultimately, I was able to apply the energy momentum principles to prove that no work was done in the system, and created a computational model to predict the motion of mass oscillating on a spring by applying concepts such as gravitational spring, potential energy, kinetic energy, and force due to gravity. Thank you.